Good afternoon, everyone. For the next 1 hour, get ready to delve into the modern world of multiphysics modeling world. My name is Manpreet Kaur, and I will be moderating this exciting live webinar titled Multiphysics Modeling of Electronic Components with COMSOL. Not wasting any more time, I take this opportunity to introduce our esteemed speaker, Kavitha K, who is the technology specialist in COMSOL. To give a brief introduction about Kavitha, Kavitha received her master's degree in electronics and communication, specializing in microwave and radar engineering from Cochin University of Science and Technology, Kochi. Her experiences include research at Raman Research Institute, where she worked on design and analysis of frequency-independent antennas for cosmological experiments in radio astronomy. Besides this, Kavita has also worked on characterizing RF receivers system for radio astronomy applications. During the webinar, requesting everyone to share their questions by writing in the chat box. Also, we will be conducting polls during this 1 hour webinar, so don't forget to share your opinions. We will be providing the information about the presentation on demand after the webinar. You can share your interest to us by writing at info@theworldpost.com. Subject presentation information of COMSOL webinar. And now, allow me to welcome our esteemed speaker, Kavitha K, who will be starting the presentation and sharing live demonstration during this 1 hour webinar. Ms. Kavitha, requesting you to share your screen and start the presentation.
Yeah, I have shared my screen. Hope the screen is visible. Hello, everyone.
Yes, the screen is visible, Kavitha.
Yeah, sure. Yeah, thank you. Yeah, hello, everyone. Greetings from COMSOL team. So I'm Kavitha, and I extend my warm appreciation to everyone participating in this webinar on multiphysics modeling of electronic components with COMSOL Multiphysics. Today, we will talk about how COMSOL Multiphysics Simulation tool will be helpful to perform multiphysics simulation of various electronic components. We will be looking at various types of electronic devices and different aspects of simulation of electronic devices using COMSOL Multiphysics, and how a multiphysics simulation can help you design and optimize your electronic devices and components for real-world application. Yeah, we'll start. So modeling and simulation has proven to be a very powerful asset in design and manufacturing of electronic components, enabling engineers to tackle key questions related to component performance or efficiency while they foster innovation. So the main motivation behind today's topic of interest is to elaborate on the capabilities of COMSOL multiphysics simulation software, how the software can help you model wide range of physics phenomena with respect to electronic devices, and how it can enable you to precisely prototype your electronic components, along with the environment in which these components are working can also be simulated. So as the name suggests, COMSOL is a multi-physics simulation software where you can simulate various physics areas such as electromagnetics, fluid flow, heat transfer, structural mechanics, acoustics, chemical, etc. You can simulate for each of these physics independently, or you can couple multiple physics equations and solve a multiphysics model. And these multiphysics simulation you can perform using a single graphical user interface, that is on a single GUI, using a single modeling workflow. Irrespective of the physics that you solve for, your modeling workflow is also going to be the same. So that is the beauty of the tool. So before moving on to today's topic, so we would like to understand the experience of today's audience with the usage of simulation tools. So we would like to know whether you are a regular user of simulation tools. So we are launching a poll question here to know whether you are a regular user of simulation tools, or you are evaluating simulation tools for your ongoing or any of the upcoming project, or you are attending the session out of your personal interest, or you are user of simulation tools, but you are new to multiphysics simulation. So I would request all the participants, the attendees of the webinar, to answer the poll question. I request the attendees to answer the poll question so that we'll have a clarity or background of today's attendees on usage of simulation tools. I'll wait for 1 more minute, then thereafter we can proceed. So thank you for answering the poll question. So we'll move on. Yeah. So to start with, since we discussed about what COMSOL Multiphysics simulation tool is and it can cater to different physics areas, so COMSOL has various modules to address different physics areas of simulation, and here are few of the modules that might use when modeling the electronic devices. So the first one that you see here is the AC/DC module, which will be predominantly used for modeling power electronic devices or low frequency electromagnetic devices. So you can model devices such as transformers, coils, model inductive, resistive, or capacitive devices, electromechanical devices, all components of your power engineering applications. And you can also simulate Joule heating and induction heating phenomena as well. So the next one, what you see here is the heat transfer module, so which you can couple with the electromagnetic physics to study the electromagnetic heating effects. So if you are interested in convective heat transfer to the surrounding fluid domain, so mainly for electronic system cooling, then you can also consider the conjugate heat transfer here. So next, when you are solving electromagnetic problems, so there can be situations where you have electromagnetic forces like Lorentz force or Maxwell stress, and your structure might deform. So then you can couple electromagnetic physics with the structural mechanics, and you can also account for temperature rise due to thermal expansion as well. And next, you have the RF module. So where you can model, so using RF module, so you can model devices, passive devices in the RF regime. So where you can simulate for electromagnetic wave propagation and study resonant devices, model RF and microwave heating applications. And here when you are modeling RF applications, say it can be passive devices or antennas, etc. So you can also couple with your external circuits as well. And towards the end, you also have the semiconductor module to model and simulate semiconductor devices at the fundamental device level, like design of transistors or diodes or optoelectronic devices, etc. So moving on here, I would like to launch another poll question. So this is mainly for us to understand the area of the which area of application you are interested in. So whether you are a user who predominantly works on power electronic devices, or you are interested in modeling electromagnetic heating effects for your electronic devices, or you are interested in modeling thermostructural effects of electronic devices or PCBs, or if it is any other topic of interest related to modeling electronic devices, so you can mention that as well in the questions tab. So I would request the attendees to answer this poll question. I could see most of the attendees are interested in modeling electromagnetic heating applications for your electronic devices. I'll wait for a minute or two, then we'll proceed. Okay. Thank you for answering the poll question. Let's move on. So I'll start with the low frequency electronic devices. So where like we saw that you would be predominantly using the AC/DC module. So you can model capacitive devices, inductive devices, or resistive devices, or even electrical circuits. So when talking about capacitive devices, so you can perform electrostatic analysis focusing on evaluating capacitance, or to investigate the electric field distribution around your model, or you can study the topics such as like charge distribution on your device, or dielectric laws, or evaluating electrostatic forces, or to understand the risk of electromagnetic breakdown. So for all these, so you can use the electrostatic analysis. And for inductive devices, so you can investigate electromagnetic fields coupled with currents. So frequently studied phenomena here are skin effects, proximity effects, heat dissipation, and in general parasitic inductive effects such as crosstalk and mutual inductance. And the resistive analysis here mainly focuses on current density distribution, and the most common use case here is to find the hotspots in a conductor design. So here you can see an example of a bus bar geometry. So here mainly the interest is to find the temperature hotspots in your conductor design, or you might be interested sometimes to evaluate just the overall performance or heat dissipation, or just calculate the lumped resistance. So these are different topics that you might be interested for when modeling resistive devices. And you can also have the electrical circuit formulation through which you can model lumped system of circuit elements and couple the circuit to the finite element model that you have built. And with the electrical circuit formulation, so here you can even import or export SPICE netlist. You can load a text file in the SPICE format, or you can save a text file in the SPICE format representing your circuit that you had currently modeled using COMSOL. And you also have automated circuit generation from extracted resistance, inductance, and capacitance matrix as well. So moving on, if you would want to look at capacitive effects in stationary regime, so then you would use the electrostatics physics interface, so which will also allow you to extract the capacitance matrices for the PCB. So the first example that you see here is from a COMSOL app generated from a COMSOL model. So you can find this model in the online application gallery. So this model computes the capacitance matrix of a touch screen in the presence of a human finger phantom. So where the position and orientation of the finger, so it is controlled via your input parameters. And here you can vary the electrode unit cell array size, the finger location, or the angle and the touch level, the substrate and the superstrate thickness, and their material properties. So these are the various inputs that you can give for your app and analyze the response of the device in your output. And towards the right, so if you have low frequency capacitive effects, or if you look at resistive effects and currents flowing through a PCB, so then you would use the electric currents interface, which will allow us to calculate current flowing through a volume and also help extract admittance when looking at low frequency capacitive effects. So talking about capacitive devices, so here is an example of a trimmer capacitor from the online application gallery. So before moving on to this example, I'm going to quickly introduce the COMSOL GUI, the graphical user interface of COMSOL for attendees who are new to COMSOL simulation tool. So towards the left, what you have is the model builder window. So the model builder window or the top ribbon tab here, both of them are going to guide you through the modeling workflow. So you can use any of one to build your model. So to quickly take you through the modeling workflow in COMSOL, so you start by defining parameters to draw your geometry, or the input parameters for excitation, etc. can be set up in the parameters. Then you draw your geometry using different geometry primitives from the geometry node, or you can import your geometry in the form of CAD format or electronic CAD format. So once you have your geometry, you assign materials to your geometry. So you have a large range of material library addressing different physics areas. So you can have your own user defined materials as well. So once you have the materials, then you set up your physics, then you mesh your geometry with respect to the physics and the study. You set up your study, so the various studies types that are possible: stationary, time dependent, frequency domain, etc. So you can set up your study and click the compute button here. So you will be taken to the results node, where you will be able to have different types of visualization for your results. So this is the modeling workflow in COMSOL as you move from top to bottom. So defining the parameters, drawing geometry, assigning materials, setting up physics, meshing the geometry, computing the study, and visualizing the results. So any option that or any node that you choose in the model builder window, the appropriate settings are here in the settings window. And towards the right, what you see is the graphics window, where you will be able to visualize your geometry or mesh or the results. And here towards the bottom right corner, which is currently hidden here, so you will have an information window that will house the message window or the progress information. And if you evaluate any of the results in the form of tables, so they get displayed in the information window. And the same modeling workflow that we saw through the model builder window, so the same can be guided by the top ribbon tab as you move from the left to right. So this is the quick overview of COMSOL graphical user interface. So the example that you see here is an example of a trimmer capacitor. So this example models an adjustable capacitor, so which uses, here you can see the parallel facing electrodes with a certain amount of variable overlap area here. So the implementation of this capacitor in COMSOL uses electrostatics interface. So along with this, so you have a parametric sweep to rotate. Here you can specify, rotate the screw and vary the electrode overlap area. And so you can do a stationary analysis for your electrostatic physics. So moving on, here we have a user story, one of the success story from Cypress Semiconductor. So they design capacitive touchscreens for various applications such as smartphones, automotive environments, MP3 players, household appliances, etc. And all requires, so different applications, they require different designs, and they must perform well under challenging operating conditions. So that is what they wanted to test for in the simulation environment. So they mainly wanted to understand the electrical performance of different screens, optimize designs to maximize the performance and minimize negative effects of variables such as what can happen when a sticky or wet hand is brought in contact, or to understand the physical contact with different surfaces, or if a water is in contact with the screen, so what happens. So they want to simulate for different scenarios or the worst case conditions that can affect the performance of the touch screen. So they had used COMSOL Multiphysics to understand the electrical performance, measure the change in the mutual capacitance when a stylus or finger presses the screen. So they had also tested for different thicknesses, permittivities of various layers, different parameter changes and touch positions as well. So they also use the application builder of COMSOL. So COMSOL has a model builder to build a model, and from the model builder, so you can build an application or an app similar to a mobile app using the application builder, and you can generate an app something similar to the screenshot that you see here towards the top right corner here. So you can see that app does not need any information of the modeling environment. So here, this is how our modeling environment looks like. And the person who builds the model or designs the model needs to have idea about the simulation software. Whereas when you use the app, you need not have an idea. The person who is using the app need not have any idea about the modeling software. So they will just play with different input parameters, and they will analyze how the variations of the input parameters or the conditions, environmental conditions, how they are going to affect the output results. The output results can be in the form of a image in the graphics window, or it can be in the form of a table, or it can be just a number displayed, so or different types of plots. So this is how an app environment looks like. So you just have input and output. So they had used this application builder to create a simulation app from the COMSOL model, so that can be used by their colleagues and customers to easily verify new design ideas and try out different operating conditions, etc. And they also use COMSOL server to deploy their custom app to colleagues around the world. And so this allowed them to access apps using a Windows-based client or a web browser platform. Yeah. So moving on, so we talked about the capacitive devices. Moving to the resistive and inductive devices. So COMSOL again has a wide range of functionalities for modeling the resistive and inductive devices for any type of application. Can be for power distribution or material processing, sensing or heating, etc. And here are few screenshots or from different examples from our online application library to highlight few. So here you can see an example of a power inductor, so which we will see in the upcoming slide. So here you can see an example of a bus bar connected mainly, which is mainly used for electrolysis process. Here mainly you are analyzing the resistive heating to mainly understand where are your temperature hotspots. So here you have an example of a silicon carbide epitaxial furnace. So again, you can study your inductive devices. So moving on to an example on one of the inductive device. So here you have an example of a power inductor, so which is widely used in switch power supplies and DC-DC converters. So here towards the right, you can see a screenshot of the magnetic and electric fields interface, so which shows you a frequency domain study for this device. So you can study the capacitive and inductive effects and also the resonance at some frequency. So here the picture, what you see in the graphics window is a single conductor of 2.5 turns with a magnetic core. So here, for example, instead of 2.5 turns, say that we have a 100 turn coil or a lit spire configuration. So in these scenarios where we might have complicated coil geometries or large number of turns, so for this, COMSOL has a dedicated coils feature, so where you have various options to select whether you want to model a multi-turn coil or a homogeneous multi-turn coil, and you can apply any number of turns you want in the settings as well. So moving on, there is another user story. So this is from APEI, which stands for Arkansas Power Electronics International. So they are developing new packaging designs to improve the performance and thermal management of power electronic devices operating under extreme pressures and temperatures. So according to simulation, the APEI power modules, they had lower thermal resistance and significant lower thermal inductance compared to a common transistor like TO254 that you see here. So using COMSOL Multiphysics, so they have found the most influential parameters that affects the inductance value, such as it can be the size of the device, the thickness of the base plate, etc. So for this, they had used the uncertainty quantification module of COMSOL to find which are the influential parameters that can affect the inductance, and they had chosen appropriate parameters such that they keep the numbers under control and optimize the power modules accordingly. So the COMSOL Multiphysics also allows importing and analyzing geometry of printed circuit boards or ECAD models, electronic CAD models, through its electronic CAD import module, supporting various formats like GDS2, IPC 2581, ODB++, etc. for importing PCBs, ICs, IC layouts, and MEMS devices, so that you can run electromagnetic simulations, heat transfer, and more. One of the common objectives of electromagnetic simulation is to extract the lumped quantities in the form of resistance, inductance, or capacitance matrix that can be used in electric circuit simulations. So here you can easily extract lumped quantities for electrical circuit simulations in COMSOL using the circuit extractor add-in. So this add-in offers you an easy way to directly convert the results of electromagnetic simulations into an electrical circuit physics interface, and then subsequently you can also export it as a SPICE file, SPICE netlist file. If you are interested in calculating the capacitance matrix or inductance or resistance matrix, so you would use the appropriate interfaces. Say for example, capacitance matrix, so then you would use the electrostatics interface. Say if you would like to extract the resistance and inductance matrix, so then you can also use the magnetic fields current only interface. So you have different interfaces according to the type of results that you would like to evaluate. So moving on and talking about electromagnetic losses. So a minimal electromagnetic heating model must consist of the following, say one physics that solves for the temperature field, and another physics that solves for electric and possibly magnetic and also including losses, and a feature that couples both of these physics together. So here you see an example of a thermal actuator. So though this includes the electric physics, the physics for your electrical application. So here basically the electric currents, next the heat transfer physics, and also solid mechanics. So talking about first the electromagnetic heating, so which includes electric currents and heat transfer. So there are two types of electromagnetic heating phenomena that you can capture using the low frequency electromagnetic physics module. One is the Joule heating. So you have the dedicated Joule heating interface, the multiphysics coupling to model resistive heating and heating due to dielectric losses. So this multiphysics interface, so once you choose the Joule heating multiphysics interface, so it automatically adds electric current interface and heat transfer in solids. So the multiphysics coupling adds the electromagnetic power dissipation as a source of heat, and the electromagnetic material properties here can depend on temperature. So different dielectric and conduction models are also available for the electric currents interface. And you can also use the induction heating interface to model induction and eddy current heating. So this multiphysics interface, again, it is very useful for capturing the induction heating phenomena. And whenever you are working on electromagnetic heating applications, similarly, you can also simulate microwave heating and RF heating as well. And when you are working on electromagnetic heating and you would like to evaluate electromagnetic losses, so you can also include a loss calculation sub-feature. So depending upon the physics interface that you would use, so you can add a loss calculation sub-feature to compute the copper loss due to resistive heating or iron loss due to hysteresis or eddy current or other effects. So moving on, so next we are moving to simulate a much bigger picture, so where you could simulate multiphysics coupling for power electronic devices. So in the middle we have the electromagnetic fields here coupled with electric circuits. So which is the main focus of electronics, or here in this example, say the power electronic simulation. Looking towards the left here, we have the EM forces or Lorentz forces, and there could be some deformation. So then you can couple with solid mechanics module. So the electromagnetic fields with electric circuits can be coupled with solid mechanics module to study the deformation. And if the deformation is going to in turn affect the electric and magnetic fields again, so then you can establish a two-way coupling here. Additionally, you can also study the acoustic structure interaction, which allows you to study the interaction of the elastic waves in solids and pressure waves in fluids. Next, to understand the temperature distribution and check for potential thermal damage, so you can couple with the heat transfer interface, so where EM losses will be the source of heat for the heat transfer interface. Also here, if the material property is going to be a function of temperature, then you can do a two-way coupling here as well. So next, if you have thermal expansion, so then you might have to couple all three of them together, say the electromagnetic fields with heat transfer coupled with solid mechanics to capture the thermal expansion. And in case if you would like to simulate the convection with the fluid medium or a surrounding fluid medium, the medium can be air or liquid, can be also used as a coolant. So then you can use the conjugate heat transfer, coupling the heat transfer with computational fluid dynamics. And you also have an optimization module on top of these, so where you can perform the device optimization. So the optimization can be for any of the single physics that you work on, or the optimization can also be performed on a multi-physics simulation as well. So moving on, again we have a user story here relevant to electromagnetic heating application. So this is from ABB Semiconductor. So their team has been using COMSOL for multiphysics simulation to understand electrical, thermal and electrical mechanical response for different IGBT modules. So the challenge for them was to improve the lifetime of the power module that you see here, so which are composed of many parallel insulated gate bipolar transistor chips. The IGBT chips is what you see here. So they had explored different methods for improving the design with experiment and simulation, and they were evaluating various configurations to connect wires to the emitter to see if stitched bonding techniques could extend the lifetime of the device. So they turned to multiphysics simulation to gain an explanation for the experimental performance of the IGBT chips. Also, they had also used the simulation tool for understanding different bonding layouts for the wires, and this helped them reduce the time spent on repairs and also helped them to take efficient methods in the initial stages of the modeling phase itself, so that they can appropriately model efficient power module. So next we will look at the heat transfer mechanisms and COMSOL capability to model these mechanisms for electromagnetic heating application. COMSOL supports modeling of heat transfer through conduction, convection and radiation. So the materials for your conduction simulation can be isotropic, anisotropic, linear or non-linear. You can define thermal contacts, and you also have dedicated features for modeling thin layers as well. You can also model free or forced convection either in laminar or turbulent regime. And moving to radiation, so regarding radiation, you can model surface to ambient and surface to surface radiation. So further looking at cooling electronic components along these aspects, so if you want to incorporate a cooling mechanism for your electromagnetic devices, so there are dedicated features again here for in COMSOL for modeling this. So for example, you can use the functionality to model fans and grills in your design. So you can define them on inlets, outlets or interior boundaries. You can also input the data from various, you can input the data from fan curves from manufacturers of the fan. If you rely on, say, heat sinks, you may have very thin fins. So you can model heat sinks or you can model thin fins. You can model this using heat transfer. Say, for example, you're modeling very thin fins. You can model this using heat transfer in shells interface, which means fins will be represented by boundaries instead of very thin volume. So you can avoid meshing of the volume and thereby reduce the cost of the computation. And further, you can also model porous media in simulation and use the fluid properties from the thermodynamics database or from the moisture transport features. So moving on, next we have another user story from Bosch, where COMSOL simulation has been used to improve their product design. So COMSOL here had helped them to identify potential, again, temperature hotspots in their early development process of their device to avoid failure that can cause any potential thermal damage. So compared to their previous designs, the optimized inverters have 6% greater range and 200% jump in the power density. So this was possible for them to identify the potential hotspots and place the critical components away from the hotspots so that they can avoid potential thermal damage. So when temperature fields vary, you might have deformation of the structure. So this is again the same example that we saw in one of the earlier slides on thermal actuator. So where we discussed about electromagnetic heating, say where you had electric currents with heat transfer, coupling the power dissipated from electromagnetic physics as the source of heat for your heat transfer in solids. So now if you are interested to understand the thermal deformation, so then you can add the solid mechanics physics interface and you can just include the thermal expansion multiphysics coupling node so that you see here. So this will enable you to compute the thermal stresses in your devices, whether you are working on solid or thin structures. So you can simulate the thermal expansion effects. And here again, your material properties can vary with temperature. So moving on, the electronic equipment often has to be certified to function after having been subjected to the specified shock load. So performing a numerical simulation is often cheaper than a physical test when you want to study for the shock response. And this the way of simulating this in a simulation environment will also have a shorter turnaround time. So in many cases, it is not necessary to perform a full nonlinear contact analysis. So the shock is not studied not by dropping the component here, but rather by attaching it to a rigid frame having a given acceleration history. So a common such specification of a shock is that your acceleration behaves as a half sine function with a given period and peak amplitude. So that is what is modeled in this example. So the effect of a 50-gram half sine shock load with a duration of about 11 milliseconds on a simple computer motherboard is what is investigated here. And the image or the picture that you see in the graphics window here is the screenshot of the vertical displacement as a result of response spectrum evaluation, the shock response spectrum. So yeah, this is the vertical displacement plot. So next we will see few other structural mechanics simulation that is helpful for electronics application. So the first one that you see towards the left here is the reflow soldering of an integrated circuit. So we are modeling the chip or couple of chips being attached to a PCB by reflow soldering. So the purpose of the simulation model here is to evaluate the residual stress and warpage of the PCB during this process, which occurs by thermal expansion of different materials. And next towards the right here, what you see is a screenshot of an application library example solving for a simulating for a 4-point bending test of an IGBT module. So this is a classical standard mechanical test. So on this picture, what you see is a IGBT module with 6 unit modules here. So these are there are 2 fixed rollers below this module. So you can it's slightly hidden. So 2 fixed rollers below this module, and on the top you have rollers where we apply pressure. So the goal here is to evaluate the maximal strength of the IGBT module and assess the warpage of the module. So with regards to electronic device testing, you can also perform EMI EMC test. So where you can perform emission, immunity, and susceptibility of electronic devices can be evaluated using COMSOL. So here in the left, what you see is a model of a circuit board in a plastic enclosure finished by a incomplete conductive walls or a conductive enclosure. So the conductive enclosure is incomplete, and this is working in the range of 2 to 6 gigahertz. So the enclosure here is surrounded by air and located next to a dipole. So a dipole antenna is placed next to this model. So there are two types of study involved here. The first one is to evaluate the basic radiated emission through the incomplete shield when one of the microstrip is excited. What is the radiated emission? And another study is to evaluate the immunity response of the circuit board. So we have an antenna mounted outside this enclosure, and there is external radiation from the antenna, and how immune is this board with respect to the external radiation is what is evaluated here. So towards the right, what you see is an example from electrostatic discharge. So the RF module in COMSOL provides you with a dedicated interface, electromagnetic waves transient physics interface, which provides 4 predefined electrostatic discharge currents according to different standards. So these standards are like human body model, machine model, charged device model, and extended human body model. So you have the electrostatic discharge currents according to different models that you want to analyze for. Yeah, and you can analyze for the electrostatic discharge effects. So moving on to the aspects of semiconductors, so COMSOL covers a broad range of physics, and so when coming to semiconductors as well, so there might be a set of users who are interested in semiconductor device processing or fabrication, and COMSOL has functionalities to perform semiconductor device processing or fabrication, and a set of users might be interested in modeling these semiconductors at fundamental device level. And again, COMSOL has a dedicated semiconductor physics interface to model the semiconductor devices at the fundamental physics level. So where you can model different semiconductor devices, transistors, diodes, optoelectronic devices, etc. Or there can be another aspects where set of users are interested in modeling the thermal management or stress analysis of the package for the semiconductor modules, which can also be performed in COMSOL using heat transfer or the structural mechanics physics interfaces. So moving on to semiconductor processing, so you can model different semiconductor processing like silicon wafer oxidation, lithography, etching, doping, deposition, etc. And depending upon the phenomena that you are capturing, so you would use the appropriate physics or interfaces and the appropriate modules respectively. Yeah, say for example, if you are working on etching the modeling inductively coupled plasma reactors or wet chemical etching, including electrochemical etching, so you would use one or combination of these modules: plasma module, chemical reaction engineering module, and electro deposition module. So moving on, next we are going to take a quick look at a demo model, which is a IGBT transistor, and I could see that most of the attendees today are interested in modeling electromagnetic heating. So this might be a very relevant example to explore today. So there is no semiconductor simulation here. So though we are simulating an IGBT module, so we are considering the electric currents interface coupling with heat transfer interface, and this model will show us how a electromagnetic heating simulation is performed in COMSOL. So let's move on to the demo now. I'll quickly switch to the COMSOL GUI. So yeah, here I have loaded, I'll just quickly reset the desktop. So this is the COMSOL GUI, which I had explained earlier, and you can see also the information window here towards the bottom right corner. So here I have loaded a model where already I have made some preparations. So we have the geometry and we also have the materials already loaded. What you see here is the model of a transistor module here in the graphics window. So here you have 4 transistors here towards the right and 2 diodes here towards the left. And we also have the materials prepared, so you can see copper on the top traces. So then you have the FR4 board, then you have the IGBT chips and the diode chip. So we don't have a physics here, and we are going to add the physics. So I'll show you how you can add physics. So let's go to the physics tab, click add physics. So what we are interested here is to model electromagnetic heating, so which is captured using the AC-DC module. So we'll go to electromagnetic heating, and we are interested in Joule heating. So you can right click and add Joule heating or to the component, or you can just double click it. So once we add this Joule heating multiphysics, automatically this multiphysics is going to add electric currents and heat transfer. So that is what is necessary for capturing the Joule heating phenomena. So now we are going to set up this physics interface. So first we'll set up the electric current physics interface. So we'll right click the electric currents. I'm going to choose a terminal here to supply current to this device. So already we have a parameter for defining the current. So I0, which I will input here. And we are going to also introduce a ground terminal. So we have introduced a ground here. So the electric current physics is set up. So next, let's move to the heat transfer in solids. So here we are just going to add heat flux boundary conditions. So our device will be heating up due to the ohmic losses of the currents that are going to flow through the transistor, and there will be a Joule heating phenomena occurring. And this will heat up our device, and also there will be a cooling mechanism. So the device will be cooled by the surrounding airflow, so surrounding the device. So the air here will convect the heat, and we can implement this using the heat flux boundary condition. So we'll right click the heat transfer physics interface, and let's add heat flux boundary conditions. And I assume here now all my exterior boundaries, the entire module is in an open environment and the air is surrounded. So we'll choose the convective heat flux, and we can write down the appropriate heat transfer coefficient, so which we have already parameterized here. So I would use the heat transfer coefficient here. Yeah. So that's all. The physics interfaces are set up, and the multiphysics interface so is automatically set up here for you. And you can just go and hit compute button in the study, and your simulation will start. Since it will take some time, so I am switching to a model, so where we have already simulated and have the results ready. So it is the same model. So where we have this terminal, and the ground and the heat flux boundary condition. And once you click the stationary study, so compute the stationary study, so you will be able to visualize the electric current distribution. So by default, so you will get these results, the electric current distribution. You can visualize the electric potential on your device, and also the temperature. So this is the temperature distribution on your device. So you can identify the major temperature hotspots, and looking upon the values, you can take appropriate measures or come up with better designs. So this is a quick introduction of how you set the electromagnetic heating problem, and it is very easier to set up here in COMSOL using a single GUI. And further, if you would like to understand the thermal deformation, so you will just add the solid mechanics physics interface, and you would add the thermal expansion, so you can fix any of the points, or any fixed constraints can be introduced in your solid mechanics, and you will just add the thermal expansion multiphysics coupling, and you can run the simulation. So the setup for thermal or thermostructural simulations are very easier in COMSOL. So that is the end of the demo, and moving back to the presentation. So here I would like to launch another poll question. I would like to know how you would like to connect with COMSOL. So you would like to connect with a COMSOL representative, or you would like to try out COMSOL for any of your project, or both of the above, or none of the above. So I would request the attendees to answer the poll question. So how you would like to connect with COMSOL? So are you interested in the COMSOL tool? So do you like to connect with any of the COMSOL representatives? So, or you would like to try out COMSOL for any of your project, or both of the above, or none of the above? So you can explore COMSOL at your own interest. So you can explore the COMSOL website. So if you have any questions, so you can start posting your questions as well in the questions tab. So meantime, we wait for the polls to be answered. You can keep posting your questions in the questions tab. Thank you for taking time to answer the poll questions. Yeah, to conclude, COMSOL Multiphysics provides different capabilities for modeling the electronic devices. So it can be semiconductor devices or low frequency electromagnetic devices. It can be resistive capacitive devices or electrical machineries, or RF circuits, or working on printed circuit boards, etc. So COMSOL provides you various capabilities. And in addition, it also has a unique functionality for multiphysics modeling, so where you can couple with your electronic device simulation with heat transfer, fluid flow, acoustics, or structural mechanics. And all these can be performed in a single GUI, the graphical user interface, and you can use the single modeling workflow to come up with a complete multiphysics simulation model. So that is the end of the session, and you can explore more visiting the COMSOL website. And thank you everyone for showing interest in COMSOL multiphysics simulation software for modeling electronic components. And I'm open to questions. I hope you all had a great session. So yeah, I'll take up the questions.
Thank you so much, Ms. Kavitha. I hope you all enjoyed this amazing presentations during the webinar and you take back home a lot of needed information regarding the subject of the webinar. Now, I open the floor for Q&A for our attendees. Please share your questions in the Q&A box. So my first question to you is, what kind of RF devices can be modeled?
Okay. So talking about RF devices, so though we mainly concentrated mostly on low frequency electronic devices, so you can model all kind of passive devices in RF or microwave regime. So you can model all kinds of antennas, all kind of passive devices like couplers, power dividers, filters, cavity filters, multiphysics simulation of RF devices like RF heating, modeling a microwave oven, or modeling how a radiation can interact with the human tissue. So RF biological applications where heat transfer and RF can be coupled. So there are various types of applications that you can model in COMSOL. So all kind of passive RF passive devices along with multiphysics simulation in RF, say with heat transfer, structural mechanics again. So when you're modeling RF transmission lines or RF boards, again you can model structural deformation of your PCBs when you're modeling the RF devices, or if you work on some cavity or resonant devices. So in those scenarios as well. So if the external temperature is changing or the RF power is large such that the cavity can deform and it can change the resonance of the cavity. So all these effects, real-time effects as well, can be captured. Harlin, I think you are not audible to me.
So the next question is how COMSOL is different across different tools available in market.
Okay, that is a good question. So COMSOL, to tell how COMSOL is going to be different compared to other tools in the market. So the first pointer is COMSOL is a multi-physics simulation software. So you can solve for multiple physics applications using a single tool, and you are going to use a single graphical user interface to capture the multi-physics simulation. Or in case if you solve for any single physics also, you're going to use the same graphical user interface. So the user interface is going to be same irrespective of whatever physics you solve for, or in case if you solve for the multi-physics simulation also, you will use a single GUI. And again, you would use a single modeling workflow. So if you are used to one of the physics, say for example, you are predominantly working on power electronic devices. Now you are having a project coming up to understand the thermal management or electrothermal and structural effects as well together. So now you can, the person who has set up the power electronic model or the device, so you can use the tool to set up the thermal simulation or structural simulation also very easily, because you're going to use the same tool. So the modeling workflow is going to be the same. And since you're using the same GUI and COMSOL has predefined multiphysics coupling, so it is easy to establish the multiphysics coupling between different interfaces. So the predefined multiphysics coupling can automatically talk between each other physics, and in that way that setting up the multiphysics problem also becomes easy. And another one more pointer that I would like to add is COMSOL also has an application builder, so with which you can create standalone apps out of your models. So you can publish this app such that the display size is suitable for a mobile, or it can be for a desktop, computer desktop. So you can have the display size accordingly. You can design the app, and so the person who is using the app or opening the app need not have COMSOL tool at their end. So they can just play with the parameters, input parameters, and see how the output is getting affected just by using the app, and they need not have COMSOL. So you can sell this app or distribute this app. You can have control to this app, like who can open the app, etc. So this is another one pointer, like how COMSOL is beneficial or how it is different.
Okay, moving forward, the next question is how well do the temperature stimulations of electronic components correlate with measurements?
Okay, so we have various verification or benchmark examples already in COMSOL application library. So I would request you can also go through our COMSOL website, and you can go to the application library page of COMSOL website. So you would find various verification examples and benchmark examples where, say, heat transfer or low frequency electromagnetics as well, where you can see the verification example, verification model section. The same you would find under the heat transfer module for thermal management as well. So in this section, so you can see that how the results. So these are verification examples where the results are matched both in simulation and experiment with a reference paper that is published, and along with the references of the paper are given. And along with this, I would also request you to go through the user story section. So I'll just quickly take you to the COMSOL website. So if we navigate to the bottom of the website, so here we have our user story. So we had seen few user stories related to thermal management of power electronic devices. So you can search for any keyword, and you can verify how the results of simulation and experiment has matched very well for different users or different industries. So this is another way you can gain confidence of how tool is better. So in most of the scenarios, they match very well. So the temperature simulations, since you are asking about the accuracy with respect to the measurements, so if you incorporate, say, in real-time scenario, the material properties are going to depend on temperature. So the thermal expansion coefficient going to be different for different materials. So the material properties are going to be a function of temperature. So if you are able to incorporate that in your material properties, so COMSOL has the equations established very well. So automatically you will be able to capture the effects very accurately closer to your simulation. So if you account for the material properties as a function of temperature, so apart from that, they are going to be like, if you ensure that, they are going to be close enough.
Okay, Kavitha. So the last question is, can we model optoelectronics or solar cell?
Yes, we can model optoelectronic devices or solar cells. So as I mentioned, so we have the semiconductor module, a dedicated semiconductor module where you can model different semiconductor applications at the fundamental device level. So it is not only for modeling transistors, diodes, etc. You can also model solar cells, optoelectronic devices, photodiodes, LEDs, etc. You can also couple your semiconductor model for optoelectronic devices with optics. So COMSOL also has optics module, wave optics, ray optics. So you can also couple with optics modules so that you will be able to evaluate for the optical response as well, or the optical output power as well. And say for solar cells also, your input light can be a function of wavelength, so which you can define manually, or you can couple with the wave optics module as well. And COMSOL has predefined multiphysics coupling to model optoelectronic devices. So where automatically there is a predefined multiphysics coupling to establish coupling between semiconductor physics and optics or wave optics, what we call in COMSOL, to model optoelectronic devices.
Okay. And thank you again, Kavitha, for answering those questions and for the great presentation. It was a pleasure to have you with us. So here we come to the end of the webinar. Thank you all for attending, and we hope you all enjoyed this interactive presentation while carrying back a gamut of information from the modern multiphysics world. The whole post appreciates feedback, so don't forget to share your queries and feedback.
Yeah, thank you everyone. Thank you for showing interest. And if you have further queries later as well, so you can write to support@comsol.com as well. Thank you everyone and have a nice day.